Next speaker is from Finland. Came here just for this meeting, so let's make him welcome. His name is Paulie Laine. He's a computer scientist, cognitive scientist, and a freelance astrobiologist. He has a position at the University of Jyvaskyla. Maybe you can correct me on that, but in Finland. He's also interested in space technology and interstellar flight, and he's going to speak on fission fragment rockets.
Hello everyone, and thank you for having me here in this wonderful workshop. I'm here to present works of authors. The reason for this introduction to fission fragment rockets is because I think they are pretty promising propulsion technology. And still you don't often see them on the list of proposed interstellar propulsion. However, we could even say that in a technological readiness level, it's in the same level as, for instance, say, laser sails, because there's no new physics needed or any breakthrough. It's well-known physics, and there is some technical issues related to that it would be a feasible proposal. Okay, here's my outline of my presentation. First I will talk about basic nuclear physics and fission fragments, and then about the proposed fission fragment rocket engines. Then I will talk about a few issues about fuel production, thermal and structural issues of the fission fragment rocket engine, and also I will conclude in the last part about the possibility of use fission fragment rocket engine in interstellar missions. Okay, everyone probably know that in fission, the fissile isotope splits into two fragments, a heavy and a light product of fission. And for instance, uranium fission release about 81% of its energy in the form of kinetic energy in these fragments. And in a usual fission reactor, this kinetic energy is harvested with the heat it generates. So there is for instance, uranium splits into light and heavy product and free neutrons. And distribution of the fission products is you can see that there's clearly two peaks in a light atomic numbers and more heavy ones. The energy is distributed also so that most of the energy, for instance in the uranium case, is released in the heavy fragment part. Now, if the fission happens near the surface of the fissile fuel, the fissile fragments could escape the fuel. And the escape probability increased dramatically when the the thickness of the fissile fuel or the size of the fuel particles approach to about 10 microns. So, and based on this knowledge, there has been a few proposed rocket engines based on fission fragments. First, Serge Dublin first proposed idea of using escaping fission fragment as rocket propulsion in 1988. In his idea, there was the design was using a rotating disc that has a thin layer of fissile material on them, and we can call this kind of design as a solid core design. Later there has been improvement like in Clark and Sheldon's proposals about dusty plasma-based fission fragment reactor, where fissile material is in the form of magnetically confined cloud of nanoparticles, and we can call this dusty plasma core design. So in the original Chaplin's idea, the fissile material is on this disk that are rotating, and one part of the disk is always inside the reactor core, where the fissile fragments are extracted to exhaust. And in the dusty plasma core, the fissile material is magnetically confined dusty plasma cloud. So what fissile material should we use in this kind of rocket engine? The fissile isotope should have a large cross-section, and its critical mass should be small to make it easier to implement in a form of rocket engine. So we can see in this list that Americium 242M isotope is ideal isotope for this kind of application of nuclear physics. There are also some others, as in other cases the critical mass becomes larger. So although both solid core and dusty plasma core can in principle operate in more abundant isotopes such as plutonium, its increased critical mass will affect the structural design. And the most optimal fuel is also the least available, the Americium 242M isotope. Normally there is a low Americium 242M abundance in nuclear waste from common light water reactors. But there is an important resonance in Americium 241 that is useful Americium 242M production through neutron capture. And the enrichment of the 242M can be done in fast reactors. And that is also a problem because we don't have so much of these kind of reactors available. So this reaction chart shows that there is a small path from 241 through neutron capture to americium 242M isotope. Okay, as I said before, other isotopes can be used also, but as their properties become less favorable as fission fragment rocket engine fuel, they are more and more easier to produce. Other isotopes with high thermal fission cross-sections are californium 251 and curium 245. Also, plutonium or even uranium can be used as in Chaplin's first proposal. And they are the most abundant isotopes, as plutonium 239 can be produced in reactor cores, and uranium 235 is a natural isotope that can be found in nature. So, as we can see, we can get plutonium 239 as a byproduct from inner reactors. Some words about thermal and structural design. As some parts of the fission fragments always collide with other fission fuel material and dissipate their kinetic energy to produce heat, the fissile material will heat up, and so some kind of heat removal system is mandatory in all kind of these designs. And in a practical level, it's some kind of radiator system. In the Chaplin's design, heat is radiated by the most of the large disks that are outside of the reactor during the rotation. And in the dusty plasma reactor design, the reactor chamber wall acts as a cooling system, partly by reflecting infrared into exhaust port. And in a solid core, they should be exposed to outer space in order to radiate the heat. And in a dusty plasma system, they should have some kind of radiators, external radiators. Okay, and in general level, structural issues are depend on reactor type and fissile matter. And roughly, we can say that more common isotope, the larger structures are needed. The components that are affected by the fissile material are the reactor core itself, the magnets for extracting the fission fragments, and the moderator, which is the largest one part in the system. Also, for longer missions, we should consider some kind of refueling system that also affects the design. In a solid core reactor, these huge disks are required, and also a complex rotating system of them. And in both solid core and dusty plasma core, large magnets are required to produce magnetic fields strong enough to extract and focus fragments to thrust. And also the large moderator is required for fission reaction. Okay, some words about Fission Fragment Rocket Engine and Interstellar missions. There has been some calculations that the design becomes so large that the single-stage fission fragment rocket engine is not feasible for interstellar missions. For instance, Clark and Sheldon calculated that 10% speed of light trip to the Centauri system requires 240 tons of fissile fuel over 200 gigawatt reactor. But could we use some kind of multistage fission fragment rocket engine? Typically, this fission fragment engine has a low mass ration, but we can yet shown used reactors or moderator structures to reduce the final mass. Also, this kind of a system could eliminate the need of refueling system. And to conclude, fission fragment engine harness fission products directly. And in theoretical, we can gain a very high specific impulse in the magic number million seconds. But as Robert Werka said, still much basic physics analysis as opposed to new physics yet to be discovered remains to be done before the viability of fission fragment engine. So that was, thank you.
Have there been any trade studies done on the use of californium or curium as opposed to americium to see what would be the most economical, or is it too early for that to happen?
I haven't found any results about californium or lithium, but I think there's some kind of a trade-off between the availability and feasibility for the rocket engine.
My name is Jyvaskyla. I'm a nuclear engineer. A couple of points. You showed a picture of a probe, which I believe was a Jupiter Icy Moons Orbiter. I believe the nuclear reactor in that was not a thrust reactor, but was a nuclear reactor to generate electricity.
Right.
And it used heat pipes. The radiators you saw are the heat pipes associated with the waste heat and electrical generation.
Yeah, right. This was
Not that one.
okay.
I think it was before that. Well, maybe it's whatever it is. That right?
Oh yeah. That's right. Yeah.
That's not a propulsion nuclear reactor. That's right. And I don't believe 350 megawatts was what they were going to do on that.
Right. This is what
I think it might have been kilowatts, not megawatts.
Right. This was just the structure of the reflector structure possible.
Couple more things. Just for perspective, the 200 gigawatt reactor you were talking about, a commercial full-scale nuclear reactor in the United States is typically about 1,000 megawatts or 1 gigawatt. So you're talking about a reactor 200 times the capacity of a commercial reactor that only lasts for about 18 months before it needs to be refueled.
Right.
Okay. Third thing is that a fission event is an all-directional event. So your kinetic fragments are going to go in all directions. And so you're going to have to be able to find a way, as you said, using magnets or some kind of charged, very highly negatively charged internal structure to get all that. That's going to require a lot of power,
Yes.
as well as size. That's physics that I don't think we've done yet. I mean, I wish you luck, but
Okay. I've read some papers about the basic research done, for instance, of the Americium for electric production.
the electric production is fairly well understood, but it's very inefficient.
Move on, Pete. Okay. All right, thank you, everyone. Let's take our speakers.